Now that we understand the basics of paging, let's talk about how we protect memory in a paged environment. Memory protection is crucial to prevent processes from accessing memory that they do not own. In a page system, we can implement this by associating protection bits with each frame or page table entry. The simplest form is a bit that defines a page as either read write or read only. Every time a memory reference occurs, the hardware checks these bits. If process tries to write to a read-only page, it causes a hardware trap to the operating system. We also use a valid invalid bit. A valid setting indicates that the page is part of process's legal logical address space. An invalid setting means the page is not part of the process's legal address space. As an alternative or in addition to this, some system uses a page table length register to indicate the size of the page table. The hardware checks every logical address against this register to ensure it is within the valid range for the process. In any case, an attempt to access an invalid page results in a trap to the kernel. Let's look at a concrete example. Here we see a process with logical address space that is supposed to use addresses from 0 to 10,468. The system has a page size of 2 kilobytes. As you can see, pages 0 through 5 contain the legal addresses of the process, so their entries in the page table are marked as valid. The corresponding frame numbers are also listed. However, page 6 and 7 are outside the process's legal address space. Therefore, their page table entries are marked as invalid. If the process tries to generate an address in page 6 or 7, the hardware will see the invalid bit and trap to the operating system, signaling an illegal memory access. This scheme works well, but notice the issue of internal fragmentation. The program's legal addresses ends at 10,468, which is inside page 5. Since the entire page 5 is marked as valid, the process can technically access any addresses up to the end of the page, which is address 12,287. This happens because the memory is allocated in a fixed page unit at the end of the process does not perfectly align with the page boundary. One of the most powerful advantages of paging is the ability to share common codes between processes. Think about system libraries like standard C library, which is also known as libc, which is used for almost every program on a Linux or Unix system. Without sharing, if 40 processes were running at the same time, each process would need its own copy of libc in the memory. That is basically 80 megabyte of RAM if the library is of 2 megabyte. Instead, we can use shared pages if the code is re-entered, meaning it is not self-modifying and never changes during execution. We only need to keep one copy in the physical memory. Each process's page table will simply point to the same physical frames containing the library code. Of course, not all codes and data can be shared. Each process also has a private code and data. the process keeps a separate copy of this code and data, and the pages for this private information can appear anywhere in the process's logical address space. This diagram perfectly shows how page sharing works. We have three processes P1, P2, and P3. Each of them uses the shared library, which is libc. Look at their page tables. For processes, its logical pages for libc map to the physical frames 3, 4, 6, and 1. Now look at processes and their page table also map to their logical libc pages to exact same physical frames 3, 4, 6, and 1. So even though each process has the library in its own logical address space, they all share their single physical copy in the memory. This is an incredibly efficient mechanism for memory management.